Hello, my name's Tom Pollock, and today I'm going to demo a motor controller board that I made. This is the motor controller board that we're going to be demoing today to control a three-phase servo motor with encoder feedback in a PID loop. In this particular board we have here the connector for 50 volts, up to 50 volts, and we can vary that to change the power. We also have output for controlling each phase of the motor. There's up to 4 phases that can be controlled here. We have A, B, C, and D, and each of these outputs can pull up or down on a motor. We have our amplifier, some filter capacitors, and our microcontroller. Coming into the microcontroller, we're able to connect to the USB connector here to the PC, and we have 12 volts to power it. We have some digital I/O here that we use for plugging in an expansion board with a connector to the encoder, and we use that encoder input so that this controller knows the position of the motor. So we have some additional I/O down here, as well as some test points for the high voltage output. Here's the motor controller board, again with a heatsink mounted and the expansion port and the encoder connected up, as well as a couple probes connected to the PWM-A and PWM-B output that we can watch on the oscilloscope. Okay, so this is our test motor, a Sanyo Denki AC servo motor, a BL Super P5 that is a brushless motor. Take up to 3 amps, as you can see on the label. It has a 3-phase stator and a 4-pole permanent magnet rotor, and we'll be using it with a 2048 line encoder with an index mart. If you look on the diagram here, we're considering a simplified version of a motor, which we use in our theory. We have an A coil and a B coil and a C coil that are connected in the center, and then also in the center is a rotating magnet. In this case we're showing just a single magnet, 2 poles, north and south, and by energizing these coils in different ways we're able to make the motor turn by having this magnet line up with the coils. Typical case would be current coming in from A and then splitting out, going out B and C. You can also go the opposite way, and by permutating this current condition around on the B and C connections as well, we end up with 6 equally forceful positions that we can control the motor with. In actuality, when we rotate what looks like once on this diagram, the motor rotor actually rotates only halfway, so we have to rotate twice in order to get a complete rotation of the motor. This is an application written in C++ where we can move the motor shaft and we can read the encoder's position as well. I've got the position encoding in the parenthesis next to the position, and when I move the shaft you can see the position change. The expansion board LED can also be turned on by putting a 0 in the I/O box. So we have the I/O box, it's already got a 0. If I click change I/O and look down the expansion board, when I click the change I/O button, the light comes on. Go back, change the I/O to 1, back to the LED, click change I/O, turns off. Now let's use this position to move to 2048 times 10. That would be 10 turns of the motor shaft. If I push this button servo right here, the shaft will move around 10 times. We go down here, take a look at our motor. Push servo to 0, comes back, servo, servo to 0, comes back. Now, also I've got this move absolute command, and the move absolute will make a planned move where it accelerates the target position of the servo up to a certain velocity, then moves along at that velocity, and then decelerates down to the planned final position, which is 2048 0. So now I type in move absolute, and this time you see the motor move more slowly along its planned path, or move back to 0. And we'll contrast that with the servo position, which is basically saturated full force. Spin around 10 times, spin back 10 times. Now if we look at the oscilloscope, we see the pulse width modulation signal. Let's move absolute. You see the A and B signal on the pulse width modulation, and move back to 0. And you see the pulse width turn down. Now, if I put a force on the shaft, I'm going to go over here, put my hand on there, and put some force on it. So I look here on the scope, and we see as I put some force on it, the pulse width modulation builds up, and I basically am feeling a stronger and stronger force. I release, and the pulse width modulation is then reduced. Also, we have the integral portion of the PID loop set, and you can see it pulling a trim. So if I tell this thing to servo again, so it's servoing, and we look at the position, it trims it right down to 20480. I'll servo back to 0, motor stop, dead on 0, trims it out. Keep working on it and get it exactly at 0. The motor's controller system was modeled and the results were graphed. Here the yellow is the step response of the motor controller system, and the magenta curve is the integrator output with the saturation showing. Thank you very much for listening.